on all scales.
Okay, thanks. Yeah, so first, thanks to the organisers for letting me come and talk about a few different things. I've chosen a title that at this point is definitely aspirational to I guess capture the range of projects that I've been working on with a wide bunch of people down here, including Sophie as well, looking at different aspects of simulating supermassive black holes and various processes involved in this. So hopefully there's something in here that you find interesting. So yeah, I'm a simulator. When we think of simulations, we might think of things like this. These cosmological boxes or zoom-in simulations. This is from the Fable suite of simulations that was specifically looking at galaxy groups clusters, and we're seeing the build-up of a cosmic time of a 10 to the 15 solar mass cluster. And when we do these simulations, as we've heard in some of the review talks, we have to include all of these different ingredients and components and different physical models and subgrid models in order to hopefully get something out of the end that looks like something we see in the real universe. And as has been highlighted, and obviously important for this workshop is including supermassive black holes, their growth and the feedback and how they affect their environments is important in simulations. To summarize this, and we've already had this in review talks last week, that supermassive black holes in particular and the feedback they inject seems to be important in these simulations for getting the high mass end of the stellar mass function right, for normalizing the black hole scaling relations, for giving us realistic looking populations of galaxies, enriching the CGM, regulating groups and clusters. And there's now a wide range. We have listed a few simulation suites and supermassive black hole physics models that have been developed that are able to reproduce a bunch of these things, whether it's through calibration or as a prediction of the model. We might also want to ask, where do these different models differ? And I think one area that has been getting a lot more attention recently is, for example, looking at the matter power spectrum and sort of comparing how does the matter power spectrum look if we include baryons and AGM feedback and compare it to a purely dark matter only universe. We'll get very different results and different levels of suppression, small scales depending on which simulation you look at. So maybe there's some avenue here if we can constrain from observations the matter power spectrum on these scales to tell us something about how feedback behaves, and also if we can do this at different redshifts to tell us how AGM feedback evolves as well. But we have a very similar slide this morning, but this was already in my here. If we want to simulate these things, we have to cover a huge dynamic range if we do want to do everything from the event horizon up to the cosmic web, back again, spanning 14 orders or more to do this. So this huge dynamic range means that this can't be done in a single simulation over the entire cosmic time. So we heard a bit yesterday about the stuff that Hopkins has been doing to really zoom in, but again, that's capturing a small fraction of the time whole universe as such. So typically you have to make a decision as to whether you want a more realistic environment with simpler feedback models, or if you want to really focus on what's going on with the feedback and accretion in detail, and perhaps with less details for the environment, more simplified environments. And so, as well as all of the physics, I think this numerical challenge has been one of the driving factors in some of the work that we've been doing in our simulations. And so one key ingredient is a refinement scheme around black holes, so super Lagrangian refinement technique. This was work done by Mike Curtis. He was a PhD student in Cambridge. This is actually nearly a decade ago now. then essentially you have your black hole in the center here. You have some region in which you can progressively increase the resolution as you get close to the black hole. This technique has now been applied in a variety of codes and types of simulations. This was originally done here to better capture the gas flows and estimate accretion rates onto the black hole, but it's also very useful if we want to model feedback as well. I'll talk a bit more. So the first specific project I'm going to talk about is jet feedback in galaxy clusters. There's a nice image of a few different clusters showing the X-ray and the radio from Rondo's review. And the nice thing about these systems is that you can see the jets. You can see that they're doing something. You can see them excavating these cavities within the X-ray, hot X-ray emitting gas as they inflate their lobes. You can often see shocks. You can see the material being moved about. I think it's visually an obvious example of the feedback doing something to its environment. You can also estimate the energetics involved. So for the cavities, you can estimate a power to be able to inflate these cavities. You can compare this to the cooling rate within these systems, and you get this correlation that's at least suggesting that the energetics involved in this feedback can balance the cooling within these systems and provide a way to prevent runaway cooling. Yeah. While the energetics seem to marry up, I think there's still something of an open question in terms of how the feedback is effectively coupled to the environment and how it can heat the environment in an isotropic manner. It's something that's still discussed a lot in the literature. From the simulation side, there's various suggestions of what process dominates in heating the environment. Things like shocks seem to be fairly common. There's more discussion around stuff like the importance of sound waves, mixing and turbulence. That in some cases depends very much on the microphysics within the intercluster medium. If you're doing the simulations, you might also want to start thinking about other stuff, fields, viscosity, the impact of realistic environments, cosmic rays, thermal conduction, things like this. And Ricardo has also worked on a bunch of this stuff as well. Thought I would just plug this review that Karen Yang and I put out, sort of summarizing the state of simulations, looking at jet feedback in galaxy clusters that discusses a bunch of these things, how they're being simulated and what the results of the simulations are currently showing. So from our side, what we wanted to do was try to bridge some of this gap in terms of what we hope is a realistic cluster environment. So taken from, say, a zoom in cosmological simulation of a galaxy cluster, but be able to invoke a more, hopefully a more physically motivated, high resolution jet feedback. So this model essentially piggybacks onto the refinement scheme, which means we have high resolution around the black hole. We can launch the jets, very high resolution. We take the resolution with it, and we can capture the jet propagation to large scales, the inflation, these low density lobes, and then look at how they interact with the environment. So here's just an example of this. So the yellow box here is just looking at the center of this cluster, where we have a black hole sitting in the middle of a fairly dense, somewhat cold disk-like structure. We can see the lobes that are inflated by this jet. In this case, we're just doing fixed power jets for a fixed amount of time, just to look at how the lobes inflate and evolve with the environment. We can see the velocity field and the complex structure that we get because we're looking at this cosmologically evolved cluster. We get all this cluster weather, this stirring, turbulence, bulk motions, and what's going on. The jets can interact with the weather. They can interact with the cold gas. So you can see that this lobe is a different shape to this lobe. Interaction. We can have a go at doing some mock X-ray observations, for example, the X-ray bright rims and the cavities from the lobes, and incredibly crude attempts at some sort of radio to look at the morphology of these as well. Yeah, so I can just play a quick movie here to show one of these cases where we have the lobe material in green, we have the hot ICM in the mustardy color, and these colder, denser structures moving through the system as well. You can see the very dynamic environment has a big impact on where the lobes end up. So, for example, this lobe gets pushed across here. This lobe ends up being disrupted by substructure. And so, in terms of looking at clusters and relic lobes, for example, if you have a particularly dynamic environment, the location of the relic lobes that you're seeing doesn't necessarily tell you anything about the previous direction of the jet, for example. But this cluster weather can also help in moderating and moving the energy around as well. So, for example, we can ask the question about where did the energy go? So going back to this motivation about how the jets actually heat the environment. So here we have essentially we've done 3 different jet powers, like a 5 times 10 to the 43, a few times 10 to the 44, or something times 10 to the 45 ergs per second. And there's a few things going on here. So I think just focusing on the solid black line in each plot, which is the energy that's retained within the jet lobe. And these are all normalized by the total injected energy. So the gray region is the period of time that the jet is switched on. We can see that for all the different jet powers, this evolution is actually quite similar. And by the end here, we've got about half of the energy in the lobes and half the energy in the environment through the work done by the inflation of the lobes in the environment. And this ratio is quite informative because if we want to, from observations, if we want to estimate the amount of energy required to inflate a lobe that we see, and this is taken to be the enthalpy, so the energy content of the lobe plus PV, this then tells you how much energy you expect to be in the lobe versus in the environment. And this gives you what that ratio should be if you're in pressure equilibrium when you inflate the if you've got a gamma of 5/3 and this is 2/3, we get a ratio of about 1. So at least in our simulations and a few others that have been finding similar ratios as well, about this sort of 50-50 split during the inflation phase in terms of energy to the environment and energy. It suggests that these are slightly overpressured, and that's what we see early on during the inflation, and they come into pressure as well. Once the jet's turned off, we then start to see some differences. So for the lower power jets, we see much more loss of energy from the jet lobes, and this is dominated by mixing. So this cluster weather aided mixing that are disrupting the lobes, and the lower power jets are much more susceptible to this than the higher power jets, which in turn can drive stronger shocks into the environment and more effective heat movement through them. So that was talking about feedback. I'll talk a little bit about accretion as well. So the go-to accretion model for a long time in cosmological simulations, although this is changing now, has been Bondi, because it's a nice simple formula with Socrates close to the black hole that you can calculate. You've got cold mass from, I think Sophie mentioned this in her review talk last week, that obviously there's a number of simplifying assumptions, and it breaks down things like angular momentum. And so we've been developing different approaches to try and model accretion. And so with as I mentioned, with the refinement scheme of the black holes that we have, we can better capture the gas flows on very small scales, and actually measure the mass inflow rates and also the angular momentum inflow rates onto what we model as a subgrid accretion disk. And so I'm afraid we're still using Purisan UIF for this. It gives very nice, it has very nice global analytic solutions that make it ideal for this sort of thing as a first step to move away from Bondi. It means we now track both the properties of an accretion disk and the black hole not only their masses, but also their angular momentum in the case of black hole spin. And involving the black hole spin is also important, right? Because it feeds into the properties of the feedback. But also, if you're thinking about black hole mergers, the relative alignment of the spins can impact recoil velocities and whether you end up with offset black holes. And this. So just a few examples where this model has been included. So this is work that's currently in prep by Yunjin Shin, who's a postdoc in Cambridge, has been looking at how can you grow black holes, dwarf galaxies, and at the moment just looking at accretion, and we're going to implement the feedback models as well on top of this. But again, with this refinement scheme, you can go down to, you end up going down to subparsec resolution, getting the formation of this nuclear gas disk that can feed a central black hole. We have star formation in here as well. And one of the interesting comparisons that Yunjin has done in these simulations is the inclusion or not of a nuclear star cluster in the center. So this is just a comparison without a nuclear star cluster and with a nuclear star cluster. And done a very nice analysis of the torque components on the gas and what's driving gas to the center of the galaxy, and finding that you get torques from the nuclear star cluster that can bring gas in and starts growing the black hole. And yeah, next stages will be to also include feedback in here to have a look at the effects as well. So we have feedback, we have accretion. We then want to couple these together. So a few years ago, now Rosie Talbot, a postdoc here from MPA, worked on coupling the jet feedback and the accretion disk models together. And the way this was done was to essentially take some inspiration from GRMHD simulations that had come up with these spin-dependent jet efficiencies, and setting the jet direction, in this case the spin direction, and looking at different scenarios. So just sort of some central gas disk, and the spin here is pointing out of the plane and driving this jet with this much recoil. In this case, the spin is initially pointing into the plane of the disk, and instead of getting this sort of classic jet-like structure, you get these massive multi-phase outflows formed that probably look more like something you'd expect from a accretion disk driven wind or some other form of feedback, maybe not on a jet. The other thing we can see is that the spin is evolving. So as this, in this case, as it's accreting from this gas supply, the spin is moving back towards the angular momentum direction of the cold gas disk here. And then following this, we implemented this model into the multi-merger simulation. So again, highly idealized setup to look at a few various things in this case. So here, this is just at a few different times. You can see the hot loads that end up being generated by jets during the merger event. The spins are initially aligned with the angular momentum vector of the disk galaxy. So these jets are pointing out of the galaxy, which means the jets don't directly interact really strongly with the gas within the galaxy. And we see that there's only a mild suppression of the star formation rates. Jets are active, and the peak here is lower by 2, I think, or so. And drop off is fairly similar. We're comparing with and without the jets. The other thing that we see with these with this feedback is that you can end up forming cold gas around these inflated lobes as they compress gas. They can then cool and fall back towards the black hole. And if you notice here, maybe this is no longer looking like this, but there's a slight tilt in here, and this is because this cold gas that's falling back towards the black hole is actually torquing the black hole spin and moving it towards the plane of the galaxy. So it accretes. Okay, we can move on to slightly smaller scales.
Yeah.
And talk a bit more about black hole mergers. So when galaxies merge, we expect their black holes to eventually make it to the center of the remnant. And there's a whole range of processes that might do this before we eventually get to the gravitational wave regime, and things like ESA in the future will be able to detect these supermassive black hole mergers. One particular thing that we've been considering is this sort of parsec, subparsec regime where we have certain binary disks. And so we did a suite of binary simulations, again in a repo, to look at different binary mass ratios, eccentricities, looking at cases where the binary is inclined to the second binary disk, looking at retrograde cases, studying the differences in things like accretion and the binary evolution. These were all done in fairly massive, self-gravitating circumbinary disks. One thing that we did notice is that, again, with this refinement technique around the black holes, means that we can capture better capture the streams in the mini disks around each component. Is that this has a telling effect on the binary evolution. So comparing without this refinement, the evolution, sorry, this is very small on here. The separation of the binary ends up stalling here, but when we have this refinement, the torques within the cavity are actually very important for shrinking the binary. This continues shrinking when we have this. And these are just a few maps, for example, the gravitational torque surface density. And we find in all of our simulations that the net torques acting on the binary are negative, driving them towards merger. This isn't necessarily a given. There are simulations looking at alternative setups and disk properties and things that do find in some situations you can end up driving by expansion due to the interaction with the second point disk. And then the other nice thing we can do given that we have the subgrid accretion disk models and tracking the spin, is to look at whether we expect spin alignment when we have these binaries and circumbinary disks. And so we can measure the alignment timescales between the spins, accretion disk, and say, do these align with each other? And do they do this on a timescale shorter than the timescale on which the binary shrinks? In all cases, we find, so for our simulations, the hatched region is a range of timescales on which the binary shrinks. The points are timescales on which alignment occurs. These are typically smaller for each given simulation than the in-spiral time, so you might expect alignment to occur. This depends very much on whether you have preferential accretion onto the primary or the secondary component. So there's some previous analytic work that we're also showing from David Rosa, where if you have preferential accretion onto the secondary, which we don't see in our simulations, low mass ratios, you don't get much accretion onto your primary, and you have very long alignment timescales instead. But for all of our cases, we have quite short alignment timescales, so we expect the spins to be aligned. Unless potentially you have simulations where your binary misaligned with the circumbinary disk, and then the accretion flows and mini disks and everything becomes much messier and all over the place. And I think there's probably more work to do on that front to study the balance. Okay, and then in the last couple of minutes, I'll just flash up a few things that are sort of in progress or future direction of stuff. So one question that often comes up with the jet simulations is, what about magnetic fields? So we've now done some simulations where we've included magnetic fields within the galaxy cluster. So here's just an example of some of the field lines sort of draping over lobes as they rise through the cluster environment. We can do a direct comparison of what the lobe looks like if you have magnetic fields versus without. You can see that this is the fields are suppressing stabilities, preventing mixing, which we can look at quantitatively as well. So the lobes live longer, retain more of their energy as they move through the system. I mentioned we were using Shakura Sinyaev. Sophie's done a lot of work on developing this unified accretion disk model that we're now starting to use in simulation. It doesn't just have the thin disk, but it has a truncated disk and an adios flow. depending on your accretion rate. And this is taking inspiration also from GRMHD simulations. If you understand how this proceeds. Finally, feedback isn't just jets in clusters. So I've also been adapting the jet model to capture wide-angled, say, accretion disk-driven winds as well. For example, looking at this in high redshift, massive halos, but this is very much early stages for this side of things. I think that's about it, so I'll stop there.
Got time for questions?
In the merger simulations, do you how far do you follow that the binary merger, the binary black holes down to? Do you get past the final parsec problem?
So I mean, so you mean in the galaxy merger simulation?
The one, yeah, I think so. Yeah, the one with the refinement. Yeah,
That one.
the one with the refinement. Yeah, that one. Yeah, that one.
Yeah,
I don't think it was the galaxy one. Yeah.
No, I mean, yeah, we run these for like 100 binary orbits.
Okay.
But we see throughout this that the gravitational torques are still there. At least, I mean, we're shrinking by like 10% over.
So what's the scale there? That's
so. I mean, the simulations are scale free.
okay.
I mean, here we've just chosen 2 10⁶ solar mass, the binary mass, so it's in the LISA.
Okay. Scale free
sort of
time scale.
parsec.
Yeah.
Parsec. Yeah.
What do you have to say about the final parsec problem, maybe from simulations like this, if anything?
Yeah, I mean, gas definitely helps with this. I don't know. I think there's been a few works recently. I think say Alessia Golandris, who's been looking more at the stellar interactions there and looking at if you properly handle the errors in the numerics of solving this, then you don't really have this. You don't really empty the loss cone, for example, in final parsec problems. It's not clear whether it's a real problem or the numerical.
While you're on this, for those of us that don't do this, why the quadruple?
You mean in here, you're just looking at the leading and trading edge of that.
Yeah, I have a somewhat generic question, right? So I'm posing it to you, but so you made a point of and you heard this many times of a dynamical range and multi-scale problem, and you also made a point of some missing physics. So what's your opinion? What matters more? What will have the biggest impact? And how do we tackle the dynamical in particular, right?
Yeah, I mean, I have my own ideas on how to tackle the dynamic range problem.
Yeah.
I'm a fan of doing these simulations on different overlapping scales, and then using those to inform. So if you can do these techniques where you resolve to smaller and smaller scales, and that tells you something that's going on the small scale, and if you get some accretion disk model or something out, then you might. And then you can also look at the feedback from this. Just come up with some model feedback. This isn't going to be easy though, because you have to couple the scales with each other. So we're definitely seeing, for example, the stuff mentioned yesterday that can go in this one direction, but then I think there is a big question about how do you then go back, because the feedback starts affecting the large scales, which then affects the small scales again. So it's an iterative process. Yeah. And as you probe different scales, you need to work with different physics.
But what matters most? What I'm saying more.
Both. Yeah, both. I'll take the easy answer, both. I mean, I think it really what question you want to answer and what scale you're really looking at. There are definitely cases where you can do your large scale cosmological simulations and you're not really worried about what's causing the feedback. You just want some energy injection that will produce something. So it definitely is a question.
I guess it's somewhat related to that. In your picture of when you combine the accretion model and the feedback, I mean, you still have to make an assumption about how you inject energy and what is the form of the energy. So did you do is there some fine tuning one way or the other about, you don't have dentist drill jets here, which would not cause any, just go through ICM like butter. And so how much of a fine tuning is involved in, maybe it's too of an honest question.
No. I mean,
But it's tricky.
yeah. So the approach of what we've been doing is to try not to kind of I mean, the thing with the sort of real jets versus light jets, this really comes from the fact that we become light jets, late lobes, and don't just go straight. So that, I think that comes down to a choice of more region. Set those, stay with the refinement. Just a model. When we did the coupling with the, say for the Blanford-Snag jets, we really just took the jet efficiencies from the simulations. In, and also we have to choose a mass loading. So we took that from the simulations and plug that in. See what happens.
One last question.
Thank you for the nice talk. So it seems how you estimate the mass accretion rate is very important in your calculations, right? So I guess you assume just Bondi Hoyle, Bondi.
Yeah, so yeah, we find a very different behavior, right? If you I mean, I don't know if just like with Bondi Hoyle, you can, as long as you have stuff there, you'll accrete, right? It doesn't really care about what direction this stuff is flowing.
Okay. Yeah, I was wondering if it's more accurate to estimate actually average mass influx rate instead of just relying on another.
Yeah, I mean, so for the model we have, so for this model we calculate the mass inflow rates.
Oh, you do not always use Bondi.
So yeah, no,
Okay.
I did that. Yeah, so in this case, we're calculating on small scales the mass inflow rates
Okay.
onto the subgrid accretion disk and the angular momentum as well.
Okay.
Let's thank Martin again.